Something unusual is happening in the outer solar system, and it centers on an object we thought we understood. Comet 3I Atlas, an interstellar visitor now moving near Jupiter's orbit, is behaving in ways that don't match the models. Its motion is drifting more than expected. Its activity is fluctuating in irregular patterns, and some of the signals coming from its direction are forcing researchers to recheck their assumptions. None of this means we're facing anything catastrophic, but it does mean the data is pushing us into territory where our standard explanations start to feel incomplete. As we break down what scientists are seeing and why it matters, take a moment to like and subscribe if you enjoy deep dive astronomy content. Now, let's look at what makes this comet so unexpectedly complicated. Orbital motion follows clear mathematical rules. When an object enters our solar system on a hyperbolic path, it is not held by the sun's gravity and will eventually leave again. In that case, its route is set by basic physics and can be predicted with high accuracy. By knowing its speed, its direction in space, and how the gravity of the sun and planets will pull on it, scientists can work out where it will be months or even years into the future. This same level of precision is what lets space agencies land robotic rovers on Mars within a distance of only a few meters of their target sites. Using these methods, scientists at the Jet Propulsion Laboratory, often called JPL, combined measurements from more than 230 observatories to compute the future path of the interstellar object now known as 3I Atlas. Their result stood out. On March 16th, 2026, this object is expected to come closest to Jupiter at about 53.4445 million kilometers, with an uncertainty of only plus or minus 60,000 kilometers. For such a distant pass, that is an extremely tight range. To see why this matters, it helps to look at something called the Hill radius of Jupiter. The Hill radius is an invisible region around a planet where that planet's gravity dominates over the sun's gravity for nearby small bodies. Inside this region, a planet can keep moons, capture passing objects, and hold them in long-term orbits. Outside it, the sun's pull wins, and most objects simply continue to orbit the sun without being captured by the planet. For Jupiter, the Hill radius on that same date, March 16th, 2026, is calculated to be about 53.502 million kilometers. The difference between this distance and the predicted closest approach of 3I Atlas is less than 60,000 kilometers, or roughly 0.1%. On the scale of tens of millions of kilometers, that is not just close. For practical purposes, it is the same distance as if the object were aiming directly for the thin shell where Jupiter's control fades into the sun's. Professor Avi Loeb of Harvard University was one of the first to point out this match. He asked what the odds would be for a random interstellar object, arriving by chance, to come this close to Jupiter's Hill radius. His estimate was about 1 in 26,000. That number already assumes that the object's path is fully natural and not guided in any special way. The Hill radius also marks the region where special gravitational balance points exist. These are called Lagrange points, often labeled L1 and L2. At these locations, the gravity of the Sun and of Jupiter, together with the motion of an object, line up so that the object can remain in a stable position with very little fuel. They are useful parking spots for satellites or probes that need a steady view. Human missions already use this idea. The James Webb Space Telescope, for example, sits near Earth's L2 point, so it can keep a clear, stable view of space with minimal fuel use. In the same way, Jupiter's Lagrange points within its Hill sphere would be excellent locations for long-term monitoring of the Jovian system. 3I Atlas is not heading for Earth's Lagrange points. It is moving toward Jupiter and will come to almost exactly the distance where those points exist within Jupiter's Hill sphere. That is why some researchers find the trajectory so interesting. A careful skeptic will still ask whether all this could simply be coincidence. The universe is large. Many objects move along many paths, and rare alignments do occur. But the Hill radius match is only one part of the story. 3I Atlas has shown several other statistical oddities. One concerns the direction from which it arrived. Its path on the sky is aligned within about 9 degrees of the direction to the famous WOW signal detected in 1977, a strong but brief radio signal that has never been fully explained. The chance that an interstellar object would come from within 9 degrees of that direction by accident has been estimated at about 1 in 170. Another oddity is its relation to the plane of our solar system, called the ecliptic plane. 3I Atlas follows a retrograde orbit, moving around the Sun in the opposite direction to most planets. Even so, its path stays within about 5 degrees of the ecliptic. The probability of that kind of alignment for a random interstellar arrival is estimated at about 1 in 500. There is also its pattern of close passes by major planets. Calculations show that 3I Atlas comes within tens of millions of kilometers of Mars, Venus, and Jupiter. Yet during the time when it was most active, near closest approach to the Sun, called perihelion, it was hidden in the Sun's glare and very hard to observe from Earth. The chance of this combination, with close approaches to several planets but poor viewing from Earth during peak activity, has been estimated at about 1 in 20,000. Each of these events by itself is unlikely, but not impossible. If you treat them as independent and multiply the probabilities together, the combined odds become very small, and simple coincidence begins to feel like a less satisfying explanation. Still, we have to be careful. Human minds are quick to see patterns in random data and to link separate events into stories. This is why science relies on careful tests, repeatable observations, and more than one line of evidence before it accepts extraordinary ideas. It is also useful to look closely at the physical behavior of the object. During its trip around the Sun, 3I Atlas showed what astronomers call non-gravitational acceleration. This means its motion did not follow exactly the path that pure gravity would predict. For comets, this is expected. As the Sun heats them, ices turn directly into gas and stream away in jets, and those jets act like weak thrusters. They give the object a small push, changing its orbit slightly. The important point is how strong that push was and in which direction it acted. JPL scientists measured a non-gravitational acceleration of about 5 × 10⁻⁻7 astronomical units per day squared for 3I Atlas during perihelion. That is a very small effect, but it is clearly visible in precise tracking data. And it turns out that this small extra force is just what was needed to shift the object's course from one that would have missed Jupiter's Hill radius to one that now meets it almost exactly. This change happened while 3I Atlas was behind the Sun from our point of view, when it could not be seen by telescopes on Earth. During that hidden period, its jets gave it exactly the course correction required to steer it toward the boundary of Jupiter's gravitational reach, not much more and not much less. Professor Loeb lists this as the 13th anomaly linked to the object, and poses a question that many scientists prefer to leave in the background. If this were a technological object designed to deliver something into Jupiter's sphere of influence, is this not the sort of trajectory you would choose? most astronomers answer with a simpler view. Natural comets and icy bodies feel non-gravitational forces all the time. The strength and direction of those forces depend on the shape of the object, its spin, its surface features, and where its active jets are located. In that picture, the path of 3I Atlas is a rare but possible outcome of these natural factors. The precise course correction is then just a lucky result of how and where its ices happened to vent gas. There is also the question of what we notice. Scientists pay special attention to objects that behave strangely. Many interstellar visitors may pass through our solar system on ordinary paths and never attract the same level of study. 3I Atlas may be a statistical outlier in a large population of mostly normal interstellar bodies. If so, it is not surprising that we focus on it and ignore the many others that leave little trace. These arguments are reasonable and deserve weight, yet they do not fully dissolve the puzzle. What we know with confidence is that 3I Atlas is heading into the boundary region of Jupiter's gravitational control with an accuracy that is hard to blame on chance alone. It seems to have made a small, well-timed change in its path while it was out of sight, of just the right size to move it onto a hill radius crossing. At the same time, observers have reported other unusual features, including complex jet structures, strange chemical mixes in the surrounding cloud of gas and dust, and irregular changes in brightness that have been tracked since July. The Juno spacecraft, now orbiting Jupiter, will be in a good position to watch when 3I Atlas makes its closest pass in March of 2026. Earlier in the year, a team of researchers that included Professor Loeb proposed a mission change that would have sent Juno for a direct intercept. That would have allowed close-up images and measurements far better than anything we can get from near Earth. The needed maneuver would have taken place in September of 2025, and that chance has already passed. Even so, Juno's instruments will still monitor the space around Jupiter and look for anything unusual as 3I Atlas brushes the edge of the hill sphere. Several outcomes are possible. Juno may see nothing beyond normal comet behavior, and 3I Atlas may prove interesting only because it came from interstellar space and followed an unlikely path. It may record signs of breaking apart or odd gas flows that allow scientists to explain the strange trajectory through ordinary physics. Or the data may show something near the hill radius that is harder to fit into current models and forces a review of how we think about objects that wander between the stars. The observations taken in this period will be important. On December 19th, 3I Atlas will make its closest approach to Earth at a distance of about 270 million kilometers. That will be our best chance to study it with large ground-based telescopes and with space observatories before it moves farther out toward Jupiter. High-resolution spectra could show whether the jets look like normal comet outgassing or more like directed thrust. Careful tracking could sharpen the trajectory and either support or weaken the idea that the hill radius match is meaningful. After that, attention shifts to March and to Jupiter. Scientists will watch to see whether 3I Atlas simply glides past the edge of Jupiter's domain and leaves the solar system forever, or whether something else happens as it crosses that invisible gravitational boundary, something we cannot yet predict. But the hill radius is only part of this story. The path that will bring 3I Atlas to the edge of Jupiter's gravitational reach is not a simple curve drawn in isolation. It is the result of a journey that almost certainly began billions of years ago in a star system we cannot yet identify, under conditions we can only infer from physics and from what we see now. Along that journey, the object we call an interstellar comet has shown behaviors that do not fit neatly with what we expect such a body to do. Since its discovery, 3I Atlas has produced jets that have caught astronomers off guard. In recent weeks, amateur observers using mid-sized telescopes have recorded details that surprised even professionals. Their images show narrow streams of material stretching millions of kilometers into space, narrow beams that remain sharply defined instead of being smeared out by the object's spin. Over exposure times that should blur any fine structure, these jets stay thin and aligned, earning an informal name among some observers, the jets that refuse to blur. On November 9th, 2025, two amateur astronomers, Frank Nebling and Michael Buchner, aimed their instruments at a faint patch in the constellation Virgo. Over about 15 minutes, they collected 5 separate exposures, each lasting roughly 3 minutes, and later stacked them into a composite image. What that composite revealed did not match normal expectations. 2 extremely thin jets reached out toward the sun, while a longer, similarly narrow structure extended almost 3 million kilometers in the opposite direction. These features were not broad fans or diffuse plumes. They looked like lines drawn with a fine needle. Experienced observers noticed something else. 3I Atlas is not a static object. From careful brightness measurements made in July and August, astronomers determined that it rotates with a period of about 16.16 hours. Spin is common among comets and asteroids, but it has an important consequence. As a rotating nucleus ejects gas and dust, the jets should trace out spiral paths, like a corkscrew, and long exposures should record this as smeared or curved structures. If you observe such a body for 15 minutes while it turns once every roughly 16 hours, you should still see some spreading of the jets in the final image. Instead, the jets from 3I Atlas remain tight and straight, preserving their narrow shapes across exposure times that ought to blur them into wide, soft fans. They reach out more than 1 million kilometers while staying as straight and focused as a beam, which does not match the usual pattern of natural cometary outgassing. Professor Avi Loeb has listed this as the 12th anomaly associated with the object. His reasoning is simple. If gas and dust leave the surface of a rotating nucleus at speeds set by normal heating of ice by sunlight, they move at around 400 meters per second. At that speed, material would take on the order of a month to travel 1 million kilometers. In that month, a nucleus spinning every 16.16 hours completes about 45 full rotations. The jet should curl into a long spiral and spread over a wide angle. Instead, the images show straight, needle-like structures. There are, in principle, natural explanations. One idea is that the jets are not steady streams, but short bursts, separate puffs of material released around the same time, giving the appearance of a continuous, narrow beam. Another is that the rotation axis is oriented in such a way that, from our viewpoint on Earth, the motion that would normally smear the jets is minimized. A third possibility is that the gas is being expelled much faster than normal thermal speeds, so it covers the distance in far less time, and the rotation does not have time to twist it into a spiral. Each of these options runs into difficulties. The discrete puff idea struggles with the fact that observations on multiple nights show very similar narrow jets. If they were brief outbursts, the pattern should change strongly from day to day as older material disperses and new ejections occur. Instead, the overall shape of the jets has stayed largely the same over weeks. The viewing angle idea requires a rather special alignment of the rotation axis with respect to Earth, another specific condition added to an already unlikely list. The high velocity idea is interesting, but raises a deeper question. What could accelerate gas to speeds many times higher than typical thermal values. Natural cometary outgassing comes from solar heating of volatile ices. The temperatures involved give molecules speeds of hundreds of meters per second, not thousands. To keep the jets as straight and narrow as we see them over such long distances would require ejection speeds far above what simple heating can provide. One possible answer, and it must be stressed that this is speculative, is some form of technological propulsion. Rocket engines and ion thrusters can produce exhaust moving at many kilometers per second, well beyond the reach of natural sublimation. A vehicle using directed thrust would create narrow, focused exhaust streams that maintain their shape because the material leaves so quickly that rotation does not have time to twist them. This is not the only way to read the data, but so far, the observations do not rule it out. The November images from the amateur community also showed another striking feature. 3i Atlas has what astronomers call an anti-tail, a jet-like structure apparently pointing toward the sun instead of away from it. Anti-tails are not unknown. In some cases, when Earth passes through the plane of a comet's orbit, dust that the comet left along its path can appear from our line of sight to project sunward. It is a trick of geometry and perspective, and it is reasonably well understood. However, the anti-tail of 3i Atlas does not seem to be just a perspective effect. When the high-resolution imaging science experiment camera on NASA's Mars Reconnaissance Orbiter observed the object during its close approach to Mars in early October, it offered a very different viewing angle. From that position, it also saw a sunward extension. That means the forward-facing jet is a real structure, with material actually extending ahead of the object along its path of motion, not simply dust seen in projection from a special angle near Earth. In standard comet science, a forward-pointing jet that persists for months would be explained by particular shapes or active spots on the nucleus, combined with its spin and its orientation to the sun. An oddly shaped nucleus, with vents in just the right places, might send material forward along the orbit. That is possible, but again, it requires a specific and uncommon arrangement, adding yet another special condition to an object that is already unusual compared with the thousands of comets we have studied. Professor Loeb has suggested another way to look at the forward jet. Interstellar space is not completely empty. It contains a thin spread of dust, gas, and occasional larger bits of rock or ice. At the speeds 3i Atlas is moving, even tiny grains could be hazardous over long times. A forward-facing beam, made of particles or energy, could in principle act as a shield, clearing or deflecting material before it hits the main body. That is very much like how engineers might design a probe intended to travel between stars for a very long time. Some form of forward protection to reduce damage from countless small impacts over billions of years. Again, this idea moves into the realm of speculation, and current data cannot prove it. But it is one more way in which the observed structures fit patterns we would expect from a guided vehicle, at least as well as they fit patterns from a purely natural comet. The jet activity seen in November of 2025 was more complicated than what had been recorded earlier in the object's passage through the solar system. On November 8th, a group of European observers took images that showed at least 7 different jets coming from the region of the nucleus, pointing in many directions. Some were aimed roughly toward the sun, some away from it, and others at angles in between. The overall picture looked, to some eyes, like a craft firing several thrusters at once. There are natural explanations for complexity too. A lumpy nucleus with many active areas, each rich in different ices and lit by the sun in different ways as the object spins, could launch jets in various directions. Other comets have shown signs of multiple jets and uneven activity, though examples with the same degree of order and persistence are rare. The rates of gas and dust loss implied by all this are high. Using the measured non-gravitational acceleration and assuming that the jets are powered by normal thermal outgassing, Professor Loeb has estimated that 3I Atlas would have to lose at least 13% of its total mass during its passage near perihelion. That is a huge fraction. If the nucleus is several kilometers across, as some brightness models allow, then billions of tons of material would need to be expelled over a few weeks. Such a loss should create a very large cloud of gas and debris around the object, detectable in spectral measurements and obvious in sharp images. The period around closest approach to Earth will be important for checking this. When 3I Atlas comes nearest on December 19th, astronomers will have their best chance to study any surrounding cloud in detail and measure how much mass actually seems to be present in gas and dust. If the observations show a dense, extended envelope, that would support the idea that natural outgassing is responsible for the observed acceleration. If, on the other hand, the expected debris cloud is weak or missing, then we will need a different explanation for the extra push the object received. The most straightforward alternative would be some form of propulsion that does not require throwing off large amounts of visible material, a possibility many scientists are uneasy even to discuss. Throughout all of this, the amateur astronomy community has been essential. Using telescopes from about 8 inches in diameter up to nearly half a meter, observers across the globe have recorded images of 3I Atlas that, in some cases, show more detailed jet structure than early public releases from NASA. This is not because space missions have failed. The various spacecraft that caught glimpses of the object were built for other tasks and only observed it briefly when their schedules allowed. Still, the contrast between the sharp, high-contrast jets seen in well-processed amateur images and the softer, point-like sources in some official material has encouraged ongoing discussion about what other data may exist and whether all of it has yet been shared openly with the public. On November 16, 2025, Japanese astrophotographer Satoru Murata recorded what many astronomers now view as the defining post-perihelion image of 3I Atlas. Using a modest 8-inch telescope located in New Mexico and a composite exposure totaling about 24 minutes, he captured the full complexity of the object's jet system. The final stacked image showed multiple jets pointing roughly toward the sun and multiple jets pointing away from it, a tightly collimated primary tail stretching millions of kilometers into space, and a bright, compact central condensation that suggested a well-defined, concentrated nucleus, rather than a diffuse, crumbling body. One day later, on November 17th, French astronomer François Kugel obtained a similar image with a 16-inch telescope. His data confirmed the same main features: sunward and anti-sunward jets, a long, narrow tail, and a bright central core. The agreement between these two independent observations, made from different continents with different instruments and processing methods, strongly argues against camera defects or software artifacts. Whatever 3I Atlas is doing, it is doing it in a repeatable, stable way, and that behavior does not fit comfortably within our usual expectations for a natural comet. This leads to a simple question that sits behind much of the current debate. Are we watching the most extreme example of a natural cometary object ever seen? One whose unusual mix of ices, dust, shape, and spin just happens to push every parameter to the edge of what physics allows? Or are we looking at something that only appears comet-like because it has built up ice and dust on its surface while traveling through deep interstellar space, masking a very different interior nature? The jet patterns alone cannot give a final answer. They can be read in more than one way. On the one hand, they may represent natural cometary outgassing, working at the limits of what is possible. On the other, they are also consistent with directed activity, such as propulsion, partly hidden behind a layer of volatile material. To distinguish between these ideas, scientists need more than images. They need spectra, detailed measurements of the light coming from the gas in the jets. Spectroscopy can reveal both what the jets are made of and how fast the material is moving. In a natural scenario, where sunlight heats ices and drives sublimation, the gas should be moving at what are called thermal velocities, typically a few hundred meters per second. This motion broadens the spectral lines in predictable ways. The overall mix of chemical species should also look familiar, mainly water vapor, carbon dioxide, carbon monoxide, and smaller amounts of other molecules commonly seen in comets. If the jets are produced by something else, the spectral pattern could look very different. Much higher outflow speeds would broaden the lines in a different way and shift some features. An unexpected chemical mix might hint at processed materials rather than untouched primordial ice. In addition, very hot ionized gas, called plasma, such as that produced by rocket exhaust or ion thrusters, can show distinctive emission lines. If we are seeing exhaust instead of sublimation, those features might show up. Powerful instruments already exist that can make such measurements. The Hubble Space Telescope and the James Webb Space Telescope both have sensitive spectrographs capable of probing faint gas around distant objects. Large ground-based observatories with high-resolution spectrographs can contribute as well, especially during periods of good visibility. It is possible that some of this data has already been collected during earlier observing campaigns, and that the community is now working through the analysis. What remains is to see what those results show when they are published and compared. As December progresses, 3I Atlas comes closer to Earth than it has been at any time since its discovery. Its position in the sky improves for many observatories, and it remains active, still producing visible jets. Astronomers have had months to plan targeted observations that address the specific puzzles raised since July. What these new measurements reveal will not only shape our view of this single object, they will influence our sense of what types of bodies may pass between star systems and what physical processes operate in those harsh environments. The unblurring jets, which stay narrow when they should spread, are sending us a message. Either they are teaching us that cometary physics can produce more ordered and directed structures than we thought, under certain extreme conditions, or they are hinting that something else is at work, something more deliberate. Both possibilities would require us to update our understanding of the wider universe. There is another piece of the story that adds weight to the questions. The period around perihelion, when 3I Atlas disappeared behind the Sun from Earth's perspective. Every comet that passes close to the Sun goes through a phase when its position puts it in line with the solar disk as seen from Earth. During that time, ground-based telescopes cannot observe it. Usually this gap is a minor nuisance. Astronomers simply connect the dots later, using data from before and after conjunction to reconstruct the missing part of the orbit and the likely brightness changes. For 3I Atlas, this invisible window was unusually significant. On October 29, 2025, the object reached perihelion, its closest point to the Sun, at a distance of about 203 million kilometers. This is when solar heating was strongest, when any volatile ices on or near the surface would have been turning into gas at the highest rates. And when most comets are near their brightest and most dynamic, it is precisely when detailed monitoring is most valuable for understanding composition, structure, and outgassing patterns. And yet, at that crucial moment, 3I Atlas was located on the far side of the Sun, hidden from Earth-based observatories. The chance that a randomly arriving interstellar object would have its closest solar approach occur exactly during solar conjunction, at the one time when ground-based instruments have the least access, has been estimated at about 1 in 20,000. On its own, that probability is not impossible, but it joins a list of other unlikely alignments already associated with this object, making the overall chain of coincidences harder to ignore. Even during this hidden phase, however, 3I Atlas did not vanish completely from human instruments. Several spacecraft designed to watch the Sun, placed at various vantage points in the inner solar system, recorded it in their wide-field cameras. The STEREO mission, the SOHO Observatory, and the PUNCH instruments all detected the object as it moved through their fields of view. Their images are not as sharp as those from large dedicated telescopes, but they still reveal valuable trends. One of the main findings from these solar observatories was that 3I Atlas brightened faster than normal models predicted as it moved toward perihelion. For many comets, brightness increases roughly as some power of the inverse of the distance to the Sun, often between -4 and -6. For this object, the best fit suggested a much steeper change, with brightness rising roughly as the distance to the Sun raised to about -7.5. That means the light output climbed more rapidly than expected, hinting at an unusual response to increasing solar energy. The color of the light changed as well. Measurements in late October indicated that the coma of 3I Atlas became distinctly bluer than the Sun. This is surprising. Dust, which makes up a large part of the visible coma in many comets, tends to scatter longer wavelengths more efficiently in the forward direction and to absorb or scatter shorter wavelengths differently, often making an object appear redder than the light shining on it. This is why Mars looks reddish, and why sunsets take on orange and red tones. In general, a dusty comet should look redder than the sunlight that illuminates it, not bluer. Some natural explanations have been suggested. Ionized carbon monoxide can emit blue light and might dominate the coma's emission under strong heating. Heavy, rapid sublimation might strip away darker surface layers and expose fresh, highly reflective ices that scatter shorter wavelengths more efficiently. Both ideas stay within known chemistry and physics, but it is also possible that other light sources are contributing. High-temperature engines, whether chemical rockets or electric thrusters, produce very hot gas or plasma that glows. The glow depends on the exhaust composition and temperature, and it can include strong emission in particular colors. A technological propulsion system that becomes active near perihelion, when extra thrust is most effective, could, in principle, produce both an unusual brightening curve and a shift in color. Again, this line of thought is speculative and must be treated with caution. The blue coloration could be entirely natural. The timing, however, is hard to ignore. The strange brightening and color change occurred at the same time that precise orbit calculations indicate that 3I Atlas experienced an extra push not explained by gravity alone. This non-gravitational acceleration near perihelion may be the most important single clue to what happened while the object was hidden behind the Sun. David Farnakia and colleagues at NASA's Jet Propulsion Laboratory reported the effect based on precise position measurements, including data from the Atacama Large Millimeter Array in Chile. When 3I Atlas came back into view after conjunction, its position on the sky was offset from where it would have been if only gravitational forces had acted. The shift was small, about 4 arcseconds, but at the object's distance, that small angular difference corresponds to a real physical displacement. By modeling this offset, researchers found that the extra acceleration could be described as having 2 main components. One pushed roughly outward from the Sun, with a size of about 135 kilometers per day squared. The other acted sideways, along the direction of the object's motion, with a size of about 60 kilometers per day squared. While these accelerations are tiny in everyday terms, acting over a period of weeks, they add up to a significant change in trajectory. Most importantly, the direction and strength of this non-gravitational acceleration are just what is needed to bring the predicted future path of 3I Atlas into near-perfect alignment with Jupiter's Hill radius. Before perihelion, using only data from July through September, the projected closest approach in March of 2026 missed that boundary. After including the extra forces inferred from the hidden phase, the updated trajectory now comes to within about 60,000 kilometers of the exact Hill radius distance. The adjustment is neither far too large nor too small. It is almost exactly what is required. If 3I Atlas is simply a natural comet, this coincidence is remarkable. Outgassing from its surface, driven by sunlight in ways we do not fully model, would have had to push the object in exactly the right directions, by exactly the right amounts, during the brief time when it was most heated and least observed, to produce the Hill radius match. It would be as if surface vents and spin just happened, by chance, to create an ideal course correction. If instead 3I Atlas is a guided object, then a small engine burn at perihelion makes perfect sense. Perihelion is where an object is deepest in the Sun's gravity well and moving fastest. A modest thrust there can produce a much larger change in the orbit than the same thrust applied farther from the Sun. This is the principle behind what is called an Oberth maneuver, a technique we routinely use in mission planning to adjust spacecraft trajectories efficiently. A craft aiming for a precise encounter with Jupiter's Hill sphere might choose exactly such a maneuver, and it might prefer to carry it out during a time when direct observation from Earth is blocked. Observations taken after perihelion add further context. As it came out from behind the Sun, 3I Atlas was still active, still emitting sharply defined jets and showing complex structures that do not match simple comet models. If the non-gravitational acceleration were caused by normal outgassing, then, as Professor Loeb's estimates suggest, the object should have lost at least 10 to 13% of its mass during the intense heating phase. If that mass left as gas and dust, it should now be part of a large expanding envelope around the nucleus, detectable as a broad, diffuse cloud in images and in spectral measurements. The next series of observations, especially those near closest approach to Earth, will be important in checking this expectation. Early amateur images from mid-November show a bright, compact central region with relatively little soft, extended material around it. The jets stand out as narrow structures rather than broad, fading shells. The overall appearance suggests that the nucleus remains more intact and less eroded than the mass loss estimates would lead us to expect. One possible conclusion is that the estimates themselves are off, and that the non-gravitational acceleration did not come from the amount of outgassing assumed. Another is that the outgassing was highly directed, producing more thrust per unit mass than in typical comets, more efficient at changing the orbit while shedding less total material. Perhaps the material that makes up 3I Atlas differs from what we normally see in comets, in ways that change the link between how much ice is lost and how much the object accelerates. Or perhaps the extra acceleration did not come from outgassing at all. Before perihelion, the Hubble Space Telescope and the James Webb Space Telescope both observed 3I Atlas, Much of that early data is still being analyzed, but what has emerged so far points to an object that does not match standard patterns. Its coma appears to be dominated by carbon dioxide rather than water, which is uncommon. Its chemical mix differs from the comets born in our own solar system. Its structure and activity do not fit neatly into any category we use to describe natural bodies. What scientists need now is post-perihelion data of the same quality to compare with the earlier measurements. They need spectra of the jets to measure both their speed and their composition. They need high-resolution images to show how much debris surrounds the nucleus, or to confirm that the expected debris cloud is not present at all. They need precise tracking so that the orbit can be refined and the match with Jupiter's Hill radius can be tested as the object continues to move. Many astronomers have marked December 19th on their calendars. That date marks the closest approach of 3I Atlas to Earth, at about 269 million kilometers. While still very far, this distance allows our most powerful instruments to gather information that cannot be collected when the object is farther out. By mid-December, the object climbs higher in the pre-dawn sky for observers in the northern hemisphere. Telescopes from Hawaii, Chile, Spain, and the Canary Islands will have their best view. Space telescopes will turn their mirrors toward this visitor for what may be the last chance to examine it in detail before it continues outward toward Jupiter. After December 19th, little can be changed. 3I Atlas will continue tracing its path away from the Sun, cooling and most likely becoming less active as solar heating falls. By the time it reaches Jupiter in March of 2026, it may be faint enough that only the largest telescopes can pick it up. But one instrument will be watching closely. The Juno spacecraft, which has orbited Jupiter since 2016, will be in position to study whatever occurs when the object moves across the edge of the giant planet's gravitational boundary. Juno carries tools that can detect changes in the magnetic field, energetic particles, and even subtle shifts in the space environment around Jupiter. It can also image at close range from a viewpoint Earth cannot match. The period behind the Sun gave 3I Atlas the chance to undergo whatever changes it did without our full attention. The encounter with Jupiter will not offer the same privacy. Observations will be recorded from orbit around Jupiter, from space telescopes near Earth, and from ground-based observatories. Whatever happens at the Hill radius will become part of the scientific record. The waiting for those moments may be the most difficult part of the entire investigation. The data collected so far contains hints, but not conclusions. It holds odd features, patterns that do not fit standard expectations, and coincidences that continue to stack up, yet none of it rises to the level of proof. For now, the object remains a puzzle, a case where current models do not fully explain what we see. The coming months may deepen the puzzle or clear it. Either path will add to our understanding. 3I Atlas may continue to surprise us, adding more anomalies and strengthening the case that something unusual is happening, or it may begin to behave in ways that match natural expectations, revealing itself as a comet from another star whose strange features arise from its long journey rather than from its nature. Both possibilities add to science. One of them would also change how we think about our place in the wider universe. The question that shadows the entire story is simple. What exactly occurred during the hidden weeks of October when the object was out of sight behind the Sun? The information we have so far raises more questions than firm answers. What we gather in December and again in March may show whether the strange behavior has ordinary explanations or whether it points towards something more surprising. This brings us to a development that received wide attention. On November 19th, 2025, NASA held a press conference that many had anticipated for weeks. The agency's associate administrator, Amit Khatria, delivered a short statement meant to bring clarity to the public conversation. His message was clear. This object is a comet. It looks like a comet, behaves like a comet, and all evidence points to it being a natural comet. The timing of this statement drew notice. For 42 days, from October 1st through November 12th, the United States federal government had been shut down during exactly the period when 3I Atlas was behind the sun. When the most important data should have been analyzed, a large part of NASA's workforce was furloughed. Instruments continued collecting data, but analysis paused and speculation spread. Once the shutdown ended and NASA scheduled its press briefing, expectations rose. Many wondered what the Mars orbiters had seen during the object's close pass in early October. They wondered what the solar observatories had recorded during perihelion. They wondered whether the spectroscopic observations revealed anything new about the jets, the nucleus, or the chemical makeup of the object. The answers NASA provided struck many observers as incomplete. The central image, shown during the briefing, came from the high-resolution imaging science experiment camera aboard the Mars Reconnaissance Orbiter, taken when 3I Atlas passed within about 30 million kilometers of Mars. High-resolution imaging science experiment is one of the most powerful cameras ever sent to another planet, able to resolve features on the Martian surface down to about 30 centimeters. At a distance of 30 million kilometers, it should still have achieved a resolution of around 30 kilometers per pixel. Instead, the image shown to the public was a blurred point spread into several pixels by spacecraft motion during the 3.2-second exposure. Arrows were added to indicate the direction of the sun and the object's motion. The coma appeared compact, perhaps 1,500 kilometers across, but no jets or fine structure could be identified. None of the known anomalies could be addressed by such an image. Professor Loeb's response was immediate. He quoted Arthur Conan Doyle's line from Sherlock Holmes, "There is nothing more deceptive than an obvious fact." His criticism was not about what NASA showed, but about what it did not show. The 12 anomalies he had documented were not discussed. The statistical oddities received no mention. The jets recorded by amateur astronomers were not addressed. The non-gravitational acceleration and the Hill radius match were left out entirely. Instead, officials repeated what Professor Loeb described as the agency's official mantra. It is a comet, it is natural, there is nothing unusual. The contrast between NASA's message and the data available from independent observers was difficult to ignore. During the same days when the agency displayed its blurred spacecraft image, amateur astronomers using 8-inch to 16-inch telescopes captured far sharper images from Earth. Their photographs showed multiple narrow jets, detailed coma structure, and a clear anti-tail. The natural question arose: how could backyard telescopes produce results that seemed more informative than a highly advanced orbital camera? The technical explanation is straightforward. High-resolution imaging science experiment was designed to observe a nearby, slow-moving surface from orbit. Pointing it at a distant object moving at high angular speed requires longer exposures and introduces motion blur. It is simply not optimized for this task. Even so, this explanation did not address all concerns. NASA has other instruments with different capabilities. The MAVEN orbiter carries ultraviolet imaging tools that could provide details about the hydrogen envelope around the object. The Perseverance rover captured images of the comet from the Martian surface. Several solar observatories watched the object as it moved near the sun. None of that material was shown. The agency stated that analysis was ongoing, that data collected by the Webb telescope in August, which should reveal detailed spectra of the coma, was still being processed, and that information from solar missions would be released later. This is the normal path of scientific work. Data is collected, studied, peer-reviewed, and published in journals where methods and findings can be examined by other scientists. That process takes time and ensures accuracy. But 3I Atlas is not a typical research subject. Public interest is unusually high. Questions are being asked in many countries, and the data not yet released may answer questions that millions of people are discussing. In this environment, NASA's caution has created more speculation rather than calming it. Congresswoman Ana Paulina Luna of Florida had already contacted NASA Administrator Bill Nelson, asking for the release of the Mars orbiter images. She also spoke with Professor Loeb and expressed concern about the lack of transparency. Whether her involvement influenced NASA's schedule or message is unknown, but the fact that congressional representatives are now engaged shows how far beyond normal scientific discussion this story has moved. During the press conference, beyond stating that 3I Atlas is a comet, NASA officials described it as remarkable, even by comet standards. They called it the oldest comet ever observed and likely the most massive of its kind. They suggested that many of its unusual traits could be explained by its extrasolar origin. In other words, because it formed around another star and has spent billions of years traveling through interstellar space, it is reasonable that its composition and structure might differ from comets that formed in our own solar system. In this view, strange does not mean artificial. Unusual can still be natural. That framing is scientifically defensible, but it also avoids direct engagement with the specific anomalies that have captured public attention. The retrograde orbit that still lies close to the ecliptic plane, the timing of its arrival that lines up close approaches with several planets, while conveniently hiding perihelion from Earth-based telescopes, the anti-tail that Mars imaging confirmed as a real structure, rather than a trick of perspective, the non-gravitational acceleration tuned to exactly the strength needed for the Hill radius encounter, and the jets that remain collimated in spite of rotation, all of these features were left unaddressed. They were not explained in terms of known comet physics. They were simply not part of the presentation. Professor Loeb has argued that this was a missed chance to engage the public honestly. When talking to a broad audience, he suggests scientists should not play down the mystery. They should emphasize it, while also being clear about what is known and what is not. People are drawn to real puzzles. If an agency insists that nothing unusual is happening when the data clearly raises questions, it risks sounding defensive. Some may begin to suspect that information is being filtered rather than shared. In response to the perceived gap, the amateur astronomy community has increased its efforts. If high-resolution images and spectra are slow to appear from official sources, citizen observers will try to fill some of that gap on their own. Coordinated networks of amateurs, working from many sites across the globe, have produced a steady flow of images tracking the post-perihelion behavior of 3I Atlas. Thanks to modern optics and advanced image processing, some of these results show details that rival or surpass early public releases. This rise in amateur capability marks a notable shift. The difference between professional and amateur observations has narrowed. As telescopes, cameras, and software have become more accessible, a committed observer with a 20-inch telescope, dark skies, and careful technique can now collect data that is genuinely useful for research. In the case of 3I Atlas, the narrow jets and complex coma structures documented by these observers can be downloaded and examined by anyone. including professional scientists. They appear on astronomy forums, in shared image repositories, and in technical discussion threads. What remains out of view for the moment is the full professional dataset that could confirm, refine, or contradict what amateurs are seeing. Spectra from the Webb telescope, the complete high-resolution imaging science experiment sequence, ultraviolet observations from MAVEN, and detailed tracking from radio and millimeter arrays, all of this exists and will eventually enter the scientific literature. In the meantime, the public sees high-quality amateur images that hint at complexity, while official channels emphasize reassurance. For many, that contrast is uncomfortable. NASA's public position is that 3I Atlas is a natural comet whose odd behavior can be explained, at least in principle, by known processes acting under less familiar conditions. Professor Loeb's position is that the number and severity of anomalies have grown to a point where alternative explanations should be considered alongside the standard one. The two sides are not arguing over raw data so much as over how to weigh coincidences, how many independent surprises are needed before the label coincidence begins to feel inadequate. The story will not remain frozen at this stage. Observations in December, especially near closest approach, will provide new tests. If they show a broad, dusty coma with velocities and chemistry that match natural models, they will support NASA's view. If they reveal further mismatches between expectation and reality, they will strengthen the case for deeper questions. The March passage near Jupiter will offer an especially clear test of the Hill radius prediction. Either the object will pass through the predicted region in a way that supports standard orbital calculations, or it will not. While we wait, one powerful tool available to astronomers is the study of the object's chemical fingerprint. Every astronomical body reflects or emits light in ways that encode its composition. When that light is passed through a spectrograph and spread into individual wavelengths, it reveals patterns of bright and dark lines. Each element and molecule leaves its own distinctive pattern, so a spectrum can be read much like a barcode. This method has been used to probe the makeup of stars, nebulae, distant galaxies, and comets for many decades. When spectrographs were aimed at 3I Atlas, the results were not entirely expected. The Very Large Telescope of the European Southern Observatory obtained spectra in the weeks leading up to perihelion. Among the emission lines it recorded was a strong signal from nickel, a relatively heavy element forged in stars and spread through space by supernovae. Nickel itself is not surprising. It has been detected in the comae of other comets. What was surprising was how strong the nickel signal was compared with iron. In most comets of solar system origin, nickel and iron appear together in proportions that match their relative abundances in the Sun. That is, the ratio of nickel to iron in their spectra looks similar to the ratio found in the solar photosphere. Both elements are released from organometallic molecules that vaporize at modest temperatures, and the physics behind their appearance in cometary spectra is reasonably well mapped out. In 3I Atlas, however, the nickel line was strong, while the iron line was noticeably weak. The resulting nickel-to-iron ratio differed sharply from what has been measured in thousands of comet spectra over past decades. This matters because the nickel-to-iron ratio carries information about formation conditions. It reflects the temperature, pressure, and chemical environment present when the solid material originally condensed. A ratio that departs strongly from solar values suggests either that the material formed in a very different kind of system, or that it has been altered in some unusual way since formation. One possibility is simply that 3I Atlas formed in an environment unlike our own, Another is that some process has enriched nickel or depleted iron in a way that does not resemble natural trends we usually see. High nickel, low iron mixes do exist in human technology. Nickel-based superalloys are used in aerospace and heavy industry because they resist corrosion and retain strength at very high temperatures. One such family of alloys, often used in turbine blades and rocket engines, is designed around this property. Another nickel alloy, known for resisting saltwater corrosion, is used in marine applications and chemical processing equipment. None of this means that 3I Atlas is literally made of such alloys. The spectroscopic measurements refer to gases in the coma, not directly to the solid nucleus. Still, the gas is drawn from the surface layers, and those layers reflect the overall composition to some degree. If the gas phase nickel to iron ratio is unusual, it is reasonable to suspect that the solid composition is unusual too. Professor Loeb has argued that this chemical pattern deserves a place on the list of anomalies. The odds that a random interstellar comet would show a nickel to iron ratio that resembles engineered materials more than natural solar system bodies are not easily calculated, but they add another piece to an already complex picture. The main counterpoint raised by other researchers is that our sample of interstellar comets is extremely small. 3I Atlas is only the third interstellar object detected in our solar system, and the first two offered limited or no information about heavy element abundances. We simply do not yet know what is normal for material that forms around other stars. That argument is reasonable. Without a baseline, it is hard to label a single measurement as truly anomalous. The nickel to iron ratio in 3I Atlas might turn out to be common among extrasolar comets, or it might be rare. At present, both options are open. This uncertainty does not erase the observation. It simply reminds us that we must be cautious in drawing conclusions from one case. The nickel behavior was not the only chemical surprise. The James Webb Space Telescope observed 3I Atlas in August of 2025 using its near-infrared spectrograph. Early analysis indicated that the coma is dominated by carbon dioxide instead of water. That is not typical for comets seen in the inner solar system, where solar heating usually drives water-ice sublimation as the main source of gas. Carbon dioxide sublimates at lower temperatures than water, so it can fuel comet activity at greater distances from the Sun. Some long-period comets, on their first trip inward, can show carbon dioxide-dominated comae when they are still far from the Sun and their water ice remains mostly frozen. In the case of 3I Atlas, however, the observations were taken at distances where water would normally be active. The dominance of carbon dioxide suggests either that the object has much less water ice than expected, or that the water is somehow prevented from turning into gas. The Webb data indicated that water made up only about 4% of the coma by mass, an exceptionally low value. Many active comets observed at similar distances show water contributing 50% or more of the gas output. For 3I Atlas, one possibility is that it formed with very little water to begin with. Another is that the water is present but locked away, perhaps buried under layers of other material, or bound in a form that does not sublimate easily, effectively removed or sequestered the water that should be present. Forming in a very cold region far from its original star could help explain why the coma of 3I Atlas is dominated by carbon dioxide. At temperatures below the point where water ice sublimates, carbon dioxide ice can remain stable, while water freezes out of the gas phase in different ways. An object that assembled under such conditions might naturally end up with more carbon dioxide relative to water. That is one possible scenario. But other interstellar visitors and many long-period comets do not show this extreme imbalance. The second known interstellar object, sometimes called 2I Borisov, had a coma composition broadly similar to comets from our own solar system. That contrast raises a simple question. Why is 3I Atlas so different? The Webb observations added another layer. They detected molecular nitrogen at levels higher than usually seen in comets. Nitrogen ice is extremely volatile, turning directly into gas at even lower temperatures than carbon dioxide. Its survival hints that 3I Atlas has remained at very low temperatures for most of its existence, preserving volatiles that would have been lost in warmer environments. This fits with estimates of the object's age. Studies of its orbit and possible stellar birthplaces suggest that 3I Atlas could be about 7 billion years old, meaning it formed well before our own solar system. An object that old would have spent vast stretches of time drifting in deep interstellar space, far from any star's warmth. In such conditions, fragile ices could persist. Age alone, however, does not explain the exact mix we see. Billions of years in the cold should affect water, carbon dioxide, and nitrogen in similar ways. It should not leave an object strongly depleted in water while keeping carbon dioxide and nitrogen relatively abundant. The pattern points back toward formation conditions, the temperatures, pressures, and chemistry present when 3I Atlas first condensed. Those conditions seem to differ from what we regard as typical for our own system. Taken together, the chemical fingerprint of 3I Atlas describes an object that is genuinely exotic. It appears to have formed in an environment unlike the one that produced our planets and comets, enriched in some unexpected volatiles, lacking others we would normally expect, and carrying heavy element ratios that do not match any known natural group. Each of these features can be given a possible natural explanation: different stellar neighborhood, different temperature range, different processing history. The universe is large, and it is reasonable to expect that bodies from other systems will not all resemble local examples. Even so, the accumulation is hard to ignore. We are not looking at a single odd measurement, but at a cluster of them, all in one object, all pointing toward conditions we have not yet directly seen elsewhere. Either the diversity of interstellar objects is far greater than we assumed, or 3I Atlas is telling us something more than a simple story of unfamiliar but natural chemistry. The spectroscopic observations planned for December will be important. As 3I Atlas reaches its closest approach to Earth, the signal becomes stronger and the opportunities for detailed spectral work improve. Better signal-to-noise ratios will allow astronomers to detect fainter features in the spectrum. Comparing the coma composition from before perihelion with the composition afterward will show how solar heating has changed the object, if at all. Shifts in the relative amounts of different gases could reveal ongoing processing, internal layering, or other forms of evolution. Of special interest will be spectra taken directly from the jets themselves. If observers can isolate the light coming from the narrow, collimated structures documented by amateurs, they can measure the chemical makeup and velocity of those jets independently from the surrounding coma. They will ask simple but crucial questions. Do the jets have the same composition as the rest of the gas, or do they contain a different mix? Are they moving at speeds that match thermal sublimation? Or do they show higher velocities? Do they display signs of unusual excitation, strong ionization, or other features that might hint at non-standard energy sources? Natural cometary jets should show certain well-understood patterns: gas speeds of a few hundred meters per second, familiar molecules, and ionization levels explainable by sunlight and the solar wind. A propulsion system would likely create a different signature: faster outflows, distinct ionization states, or spectral lines associated with specific propellants. Our instruments are capable of seeing these differences, What they cannot do is extend the observing window. 3i Atlas is already moving away from the sun and cooling. Activity will decline as the heating drops. The period during which it is both bright enough and active enough for the highest quality spectroscopy is likely limited to a few weeks. Every clear night at a large observatory matters. The chemical fingerprint already shows that 3i Atlas is not a routine object. What remains unclear is whether its unusual nature is fully accounted for by rare but natural conditions, or whether it reflects something more provocative. The spectrographs will provide their measurements regardless of how we interpret them. Whether we are ready to accept the full implications of those measurements is a separate question. Alongside these technical efforts, something else is happening that is changing how astronomy is practiced and shared. The traditional picture placed professional observatories at the top of a pyramid. Large institutions controlled access to the biggest telescopes. They collected data, processed it within their teams, and released conclusions to the broader world through papers and press conferences. Everyone else learned what they had found after the fact. 3i Atlas has become a test case for a different model. Consider the image captured on November 16th by Satoru Murata using a Celestron Edge HD 800, a telescope with a primary mirror about 8 inches across, at a remote site in New Mexico. By combining many exposures and carefully processing the results, he produced a view of 3i Atlas that revealed multiple jets pointing in different directions, a long, sharply defined tail extending millions of kilometers, and a clear anti-tail structure. At the time, these details were not visible in any image NASA had released. It is natural to ask how a telescope that might cost on the order of $10,000 can deliver results that seem richer than images from spacecraft that cost hundreds of millions. Part of the answer lies in purpose and observing strategy. The high-resolution imaging science experiment camera on the Mars Reconnaissance Orbiter took its view of 3i Atlas in a single short exposure, while the spacecraft was moving rapidly relative to the comet. Its design and operating constraints limited exposure time, and any small jitter blurred the image. By contrast, Murata collected roughly 24 exposures of about 60 seconds each and stacked them, reaching a total integration time of nearly half an hour. Longer integration builds signal and allows subtle features to emerge. Ground-based observers also have the advantage of flexibility. A spacecraft is built to serve many roles, mapping a planet's surface, monitoring weather, studying moons. Retargeting its instruments to a new, fast-moving point of light is a secondary use. The settings and modes are compromises. An amateur astronomer can tailor every aspect of the setup to the object of interest. When Elena Walter pointed her 17-inch telescope at 3i Atlas from an observatory in Chile, she could adjust exposure lengths, tracking rates, and filters solely with this one target in mind. The resulting images added to the growing body of detailed amateur data that supplemented and sometimes preceded official releases. In online communities, the response has been energetic. Forums and discussion groups share nightly updates, image processing methods, and comparisons between results obtained from different locations. Citizen scientists coordinate observing runs so that the object is watched continuously as it moves across the sky. This grassroots effort has yielded concrete discoveries. The complex, multi-jet structure seen in mid-November was mapped first by amateurs. The persistence of the anti-tail from week to week was confirmed by their networks before any professional publication. The slow changes in the coma as the object moved away from the sun have been documented in a level of detail that would have been difficult for any single observatory to match. Professional astronomers are not ignoring this work. Professor Loeb and others have pointed to amateur images as important evidence in their analyses, noting that, in some respects, the citizen dataset is more informative than early official images. The structures in these photographs are not artifacts. They repeat across independent observations, across different instruments, and across sites separated by thousands of kilometers. The features demand explanation, regardless of who first recorded them. There is, however, an inherent tension. Professional science is built around formal processes, calibration, error checking, peer review, and reputation built over many years. An image posted to a social media group does not carry the same weight as a carefully vetted paper in a major journal. Yet accuracy does not always depend on institutional affiliation. When many different observers, using different equipment under different conditions, all record the same pattern, it is hard to dismiss the result. Over time, the professional community will fully digest the data from both large observatories and space missions. Detailed papers will appear, models will be tested, the official scientific record will grow. But while that work proceeds, the richest visual archive of this interstellar object is being assembled by individuals outside traditional institutions, people driven by curiosity and equipped with tools that were once beyond the reach of anyone except major agencies. Looking ahead, this pattern is likely to repeat. The Vera Rubin Observatory, expected to begin full operation soon, is designed to scan the entire visible sky repeatedly and will likely find many more interstellar visitors in the coming years. Each new object will raise questions about where it came from, what it is made of, and how it moves. Each will attract attention from both professional teams and a global network of amateur observers ready to turn their telescopes and cameras toward the target. In that environment, the way large institutions handle data will matter even more. When the public can gather its own observations in near real time, slow or limited data release from official channels becomes harder to justify. Clear descriptions of methods, uncertainties, and results become more important when independent verification is possible. The older model, in which data remained inside small groups until publication, is difficult to maintain when citizen scientists are already sharing their own measurements and images as events unfold. The old model of hoarding data until publication simply does not work when citizen scientists are already posting their results. 3I Atlas has become a real-world test of this new way of doing astronomy. The gap between NASA's careful conservative public statements and the vivid amateur images has fed doubt among some people about official conclusions. When an agency shows a blurred point of light, while backyard telescopes show multiple narrow jets and complex structure, it is natural to wonder what else might be sitting unseen in professional datasets. That suspicion may turn out to be misplaced. Once all the professional data are processed and released, they may show the same structures amateurs are seeing, but with more precise measurements and clearer error bars. The delay could be nothing more than the normal rhythm of scientific work, slowed further by the government shutdown. There may be no active effort to hide anything at all, just the usual caution of researchers who prefer to be accurate rather than fast. Still, in a climate where trust in large institutions is already fragile, appearances matter. When there is a visible mismatch between what people can see with their own eyes and what they are being told, it creates room for alternative stories to grow. NASA's communication choices around 3I Atlas have accidentally created exactly that kind of space. Amateur astronomers, however, are not bound by those choices. They do not need permission to point their telescopes at the sky. They do not need official approval to post their images or share their measurements. They do not wait for peer review to upload their results. This broad access to observing tools is changing how unusual events are recorded and discussed. For 3I Atlas in particular, it is likely that the most complete visual record will come from the amateur community. Professional observations reach deeper and measure more precisely, but they are fewer and more scattered in time. Amateur observations are more frequent, more continuous, and often available within hours of being taken. Future historians who study the passage of the third known interstellar object through our solar system will probably spend a great deal of time looking at the archive built by citizen scientists. Some of the most informative images already come from people far outside traditional science careers. A retired engineer in Belgium, a software developer in Japan, a doctor in France who photographs the night sky after work. These observers, using equipment bought with personal savings and guided mainly by curiosity, have added real knowledge about one of the strangest visitors our system has seen. The democratization of astronomy is not total, and it never will be. Observations from space remain the realm of national agencies and large collaborations. Radio telescopes and cutting-edge spectrographs demand resources far beyond what most individuals can access. But in optical imaging, the field has become much more even. 3i Atlas shows what that looks like in practice. When official channels are slow, citizen scientists fill the gap. When professional data remain unpublished, amateur data are already circulating. When institutions say there is nothing especially odd to see, people can check for themselves. This is a healthy development for both science and the wider public. It encourages openness because institutions know that independent checks are possible. It spreads the act of discovery across a wider slice of society instead of keeping it inside a small circle. It invites people to take part directly in the process of investigation, rather than waiting passively for official statements. The small telescopes pointed toward 3i Atlas on any clear night are not only gathering photons, they are also helping to rewrite how knowledge about the universe is shared. Whatever this object ultimately proves to be, the way we have learned about it has already changed because ordinary people chose not to wait for permission to look up. Linked to this broader shift is another story that some have begun to call the Juno Gambit. In early September of 2025, mission planners faced a decision that could shape how this episode is remembered. NASA's Juno spacecraft, in orbit around Jupiter since 2016, briefly had a chance to change course, with a carefully timed burn of its main engine, delivering about 2.7 kilometers per second of velocity change. Juno could have left its current orbit and moved onto a path, intercepting 3i Atlas as the object approached the gas giant. That window has now closed without such a maneuver. The idea came from a team led by Professor Loeb, working with trajectory specialists Adam Hibbert and Adam Crow. Their peer-reviewed study showed that the orbital mechanics were favorable. Juno still had enough propellant. The required change in speed was within what the spacecraft could, in principle, deliver. The timing also lined up with the scheduled end of Juno's extended mission. The potential payoff was significant. Juno carries cameras and instruments designed to study Jupiter's clouds, magnetic field, and radiation environment. With new pointing and observing plans, many of those instruments could have been turned toward 3i Atlas. In an intercept scenario, Juno's camera system could have imaged the object at resolutions impossible from Earth. Its spectrometers could have examined the composition of the coma and jets in detail. Its magnetometer could have searched for any associated magnetic field or interaction with Jupiter's magnetosphere. Its particle detectors could have sampled, charged, and neutral particles in any extended debris region. Even a relatively distant flyby, at tens of millions of kilometers, would have provided a new perspective, viewing the object from the outer solar system instead of from near the Sun. In reality, Juno remains in its established orbit, continuing its planned studies of Jupiter. The chance to retarget the spacecraft toward 3I Atlas was reviewed and rejected. The reasons given include both technical and programmatic concerns. Juno's main engine has not been used since 2017. Earlier worries about tank pressurization and system reliability led mission managers to cancel a planned engine burn years ago. Firing the engine again after so long carried real risk. A failure could have crippled the spacecraft and ended all remaining science at Jupiter. There was also the question of priorities. Changing Juno's trajectory would have required giving up many of the observations that form the core of its primary mission. An intercept with 3I Atlas, while exciting, was not part of the original plan. Less formally, some have pointed to the political context. Because the intercept idea was associated with Professor Loeb, whose openness to technological explanations for anomalous objects has made him a controversial figure, adopting his proposal might have been seen within parts of the agency as endorsing a line of speculation they preferred to keep at arm's length. Whatever the mix of reasons, the decision was made to keep Juno as is. As a result, the encounter between 3I Atlas and Jupiter's Hill sphere will be observed from Earth and from spacecraft already near the planet, but not from a probe flying directly past the object. Juno and the European Space Agency's Jupiter Icy Moons Explorer, often called JUICE, will contribute useful data from their respective vantage points. They will not, however, provide the close-range look that an intercept would have offered. The Juno case highlights a more general tension in space exploration. Interstellar objects passing through our solar system are rare. 3I Atlas is only the third detected. The next one may not arrive for many years. When a rare event aligns with the capabilities of an existing spacecraft, there is a strong scientific temptation to act quickly. At the same time, spacecraft are expensive. Their missions are planned long in advance, and agencies are cautious about risking a functioning platform on a one-time opportunity. By the time a new plan is fully debated and reviewed, the window for action can close. As it did here, members of the United States Congress, including Congresswoman Anna Paulina Luna, urged NASA to use Juno to study 3I Atlas as intensively as possible. It is unclear whether such appeals changed any internal plans. What is clear is that Juno will not perform an intercept maneuver. The closest passage of 3I Atlas to Jupiter will occur with the spacecraft still bound to its existing orbit. It is natural to wonder what might have been learned from a closer pass. High-resolution imaging could have settled questions about the jets, showing with certainty whether they are narrow beams of material or artifacts of distant imaging and processing. Direct spectroscopy of the anti-tail could have revealed whether it is a stream of particles, a plasma structure, or something else. Sensitive measurements of the magnetic field could have looked for interactions more subtle than anything detectable from Earth. Most intriguingly, if anything unusual happens when the object reaches Jupiter's Hill radius, if material is released, if its behavior changes, if its path shifts, only a nearby spacecraft would be able to capture the full detail. Whatever 3I Atlas ultimately proves to be, the choice not to redirect Juno will likely be discussed for years. If the object turns out to be an odd but fully natural comet, many will conclude that the risk of a major engine burn was not justified. If it reveals truly unexpected behavior, the missed chance to fly a functioning spacecraft past it will be harder to accept. In that case, we will know that we had the hardware in place, the calculations in hand, and the fuel available, yet still chose to watch from afar. The European Space Agency's JUICE mission provides a small measure of consolation. In November of 2025, JUICE observed 3I Atlas from a distance of about 64 million kilometers, using cameras and spectrometers designed for studies of Jupiter's moons and environment. Those data will trickle back to Earth over the coming months as bandwidth allows. They will add to the growing pool of information about this interstellar visitor, but they will not include a close flyby. JUICE will not intercept 3I Atlas. From its current path, the JUICE spacecraft follows a gravity assist route that does not bring it close to the track of 3I Atlas. Even so, its observations have real value. Seen from a different location than Earth, at different angles relative to the Sun, and with a different set of instruments, JUICE can collect data that complements what ground-based telescopes and near-Earth observatories record. Together, these views can build a more complete picture than any single vantage point could provide. The deeper lesson from the Juno decision may be less about that one spacecraft and more about our general level of preparedness. When 3I Atlas arrived, we were not truly ready. For years, astronomers have discussed interstellar objects and proposed missions that could chase them. We already had experience with the first two such visitors, often called 1I Oumuamua and 2I Borisov. Yet when the third interstellar object was discovered, no interceptor was in place. No spacecraft was positioned to respond quickly. The European Space Agency's Comet Interceptor mission is meant to fix exactly this weakness. Once launched, it will wait at a gravitationally stable location, ready to fly out and meet a suitable target, whether that is a long-period comet or another interstellar object. But Comet Interceptor will not be operating until the late 2020s at the earliest. It could not have helped with 3I Atlas. That chance is gone. Future interstellar visitors will likely fare better. The Vera Rubin Observatory, once fully online, will scan the sky repeatedly, finding faint moving objects earlier and giving more warning time. Improvements in propulsion and mission design may allow quicker responses. Dedicated interceptors like Comet Interceptor will provide tools built specifically for rapid deployment, and the many lessons drawn from the current case will influence how such missions are planned and how decisions are made. None of that changes the present reality. 3I Atlas is following the orbit it arrived on, moving toward Jupiter and then outward, indifferent to how prepared we are. We will observe from the distances available, gather what data we can, and keep asking what might have been learned if Juno had been redirected. Ahead lies the gas giant. In March of 2026, 3I Atlas will skim the edge of Jupiter's Hill sphere, reaching the boundary of the planet's gravitational influence with a precision that looks, depending on your point of view, either like an extraordinary coincidence or the result of careful intent. Juno will still be circling Jupiter, aimed mostly at the planet's clouds, magnetic environment, and auroras. Its cameras may still catch the interstellar visitor as a moving point of light near the edge of its field of view. Its particle detectors may register subtle changes in the flow of charged particles if a debris cloud passes through. Its instruments may record hints of something we do not yet know to look for. Or later, we may look back on September of 2025 as the moment when choosing caution over risk cost us a unique chance. For now, the Juno gambit is behind us. The interstellar object continues its approach, and we remain observers at a distance, imagining the kind of close-range measurements that will never be made. What is directly before us instead is the December window. December 19th, 2025 is a key date. On that day, 3I Atlas reaches its closest approach to Earth at roughly 269 million kilometers. That is nearly twice the average distance between Earth and the Sun, unimaginably far in everyday terms. For astronomy, however, It is close enough to support detailed study before the object moves on toward Jupiter and then out into deep space. The geometry of orbits sets these chances. For much of its path so far, 3I Atlas has stayed relatively far from Earth, even while drawing closer to the Sun, and at perihelion, it was hidden behind the Sun altogether. Now, as both Earth and the object continue around the Sun, their separation shrinks to a minimum, opening a brief period of better access. During this December window, many of the world's major telescopes will be aimed at the same target. The Hubble Space Telescope can take high-resolution images in several bands of light, resolving structures in the coma and perhaps hinting at the nucleus at scales no ground-based telescope can match. The James Webb Space Telescope, if observing time is granted, can use its spectrometers to measure the composition and speed of gas in the jets and tail in exquisite detail. On the ground, large observatories like the Very Large Telescope in Chile, the Keck telescopes in Hawaii, and the Large Optical Instrument in the Canary Islands will join the campaign. With adaptive optics, they can partly correct for the blurring effects of Earth's atmosphere. With high-quality spectrographs, they can break the light into fine wavelength bins and read the chemical information encoded there. Observers will focus on several core questions. One of the most important concerns, mass loss. The non-gravitational acceleration measured around perihelion implies, under natural models, that the object expelled a large amount of material. Estimates suggest that 3I Atlas would have had to lose on the order of at least 13% of its total mass through sublimation to account for the observed change in orbit. If so, that material should still be around the object as a spreading cloud of gas and dust. Spectra and images taken in December can reveal whether such a cloud exists. If a massive, extended envelope is seen, containing what appears to be billions of tons of recently ejected matter, then the natural comet explanation gains strength. The unusual acceleration would have a straightforward physical cause. If, on the other hand, the cloud is much smaller than expected, or largely absent, then a puzzle remains. The acceleration took place. The orbit changed. If that change did not come from a huge amount of mass being thrown off, then some other mechanism must have been at work. Another focus will be the jets. The narrow, persistent jets recorded by amateurs throughout November are among the most visually striking aspects of 3I Atlas. December spectroscopy aims specifically at these structures, can measure how fast the gas within them is moving. Gas driven purely by heating tends to move at a few hundred meters per second. Engine exhaust, by contrast, can reach several kilometers per second or more. The widths of spectral lines, and in some cases small shifts in their positions, can distinguish between these speed ranges. Comparing the chemistry of the jets to that of the surrounding coma is also important. If the jets are simply focused streams of the same material that supports a natural picture, if they show a different mix of elements or molecules that might suggest a separate source or process, imaging of the innermost region around the object will also play a role. At the distance of closest approach, Hubble should be able to resolve scales of tens of kilometers. That is not fine enough to see detailed features on a small nucleus, but it can reveal whether the central region is consistent with a single compact source or multiple fragments. It can also show asymmetries in the inner coma that might hint at localized activity or structural change. If 3I Atlas is a natural comet under significant stress from heating and outgassing, it may split into pieces. If it is something else, any breakup could follow a different pattern. Careful imaging during the December window will provide evidence either way. Continuous brightness monitoring will complement these efforts. Changes in overall brightness over hours and days can reveal rotation periods, outbursts, and shifts in activity. Both professional and amateur observers will contribute measurements to build a detailed light curve. Sudden increases in brightness could mark fresh vents opening or larger chunks breaking free. Sudden decreases could mean that active regions have rotated out of sunlight, or that outgassing has dropped faster than expected. These patterns constrain models of the object's structure and how it responds to solar heating. Some observing projects will share their work in real time. The Virtual Telescope Project, for example, has announced plans for a live session on December 19th, streaming views of 3I Atlas as it passes through its minimum distance. People around the world will be able to watch as telescopes track the interstellar object, seeing updated images as they are acquired, instead of waiting for processed results days or weeks later. This is another example of the wider trend we have seen throughout this story. The tools of observation are not only in the hands of large institutions, and the flow of information is no longer one way. What observers will conclude from the December data depends entirely on what the universe presents. If the measurements support the natural comet scenario, showing a large debris envelope, gas speeds consistent with thermal outgassing, and chemistry that, while exotic, fits with plausible formation in a very cold, distant system, then the sense of mystery will soften. 3I Atlas will still be remarkable, but mainly as a rare example of material born around another star. If the measurements instead deepen the mismatch, showing much less debris than expected, jets moving at unexpected speeds, or compositions that resist obvious natural explanations, then the unanswered questions will multiply. In that case, the precise approach to Jupiter's Hill sphere in March becomes even more central as a test of competing ideas. Either way, science advances. The point of observation is not to confirm what we already think, but to discover what is actually there. In this case, the object we are watching has traveled through the galaxy for billions of years, carrying a record of conditions and processes far beyond our direct reach. Its ices and minerals hold clues to its birthplace. Its surface carries marks left by deep space over immense times. Its motion through our solar system reflects both its original launch conditions and whatever has happened to it since. On December 19th, we get our clearest view. The data gathered then and in the surrounding nights will be revisited many times in future work on interstellar objects. Researchers not yet born may study these spectra and images as they build new theories. Historians of science may look back on this period as one of the first times humanity had to seriously consider whether something from another star might not be entirely natural. For now, the practical work continues. Instruments are being calibrated, observation schedules are being set, the telescopes are preparing. The observing plans are now being locked into place. Across many longitudes and latitudes, both professional astronomers and dedicated amateurs are preparing their instruments, refining their models, and checking their assumptions as the countdown continues. They are getting ready for a moment that will not come again, our closest view of 3I Atlas, before it continues toward Jupiter and then out into the darkness far beyond. 269 million kilometers is still an enormous gulf, but it is closer than we will ever be to this visitor again. The December window is opening, and what we see through it could reshape how we think about objects that cross the boundary between star systems. This leads naturally to a question at the center of the current debate. How should we interpret the accumulation of improbabilities surrounding this object? To address that question, we must talk plainly about probability, not the informal sense of likely or unlikely that guides daily choices, but the mathematical structure that underlies how science evaluates evidence. In this framework, an improbable event is not a feeling, it is a number, expressed as a fraction or ratio that tells us how surprising the event should be under a given model. And when several improbable events occur in the same system, mathematics gives us a rule for combining them. We multiply. If one event has a probability of 1 in 100, and an independent event also has a probability of 1 in 100, the chance of both happening in the same situation is 1 in 10,000. Professor Loeb has applied this method to the catalogue of anomalies associated with 3I Atlas, assigning each a rough probability, the likelihood that a random interstellar object would show that feature. When these probabilities are multiplied, assuming the anomalies are independent, the result is a combined value so small that it raises legitimate scientific questions. The alignment of the trajectory within roughly 5 degrees of the ecliptic plane carries an estimated probability of about 1 in 500. Most interstellar objects approach from random orientations, with no particular reason to line up with the plane in which the planets orbit. The fine-tuned timing of the arrival producing close passes by Mars, Venus, and Jupiter, while also placing perihelion behind the Sun from Earth's perspective, is assigned an estimated probability of roughly 1 in 20,000. This sequence of encounters, combined with the convenient invisibility at perihelion, is not expected from a random path. The approach direction, aligning within about 9 degrees of the famous 1977 WOW signal, has an estimated probability of about 1 in 170. That could easily be coincidence, but it is nonetheless part of the pattern, the near-perfect match to Jupiter's Hill radius, an arrival missing the calculated boundary by a margin of only tens of thousands of kilometers across a span of more than 50 million, carries an estimated probability near 1 in 26,000. The non-gravitational acceleration recorded around perihelion then produced just the right adjustment to make that match exact. There is also the mass question. 3I Atlas appears to be roughly 1 million times more massive than 1I Oumuamua, and about 1,000 times more massive than 2I Borisov, while also moving faster than either. If interstellar space routinely delivered such massive bodies to the inner solar system, we should have detected more of them by now. The probability estimated for such a mass, given current detection statistics, is less than 1 in 1,000. Then there are the chemical anomalies, the nickel-to-iron ratio unlike any known comet, the dominance of carbon dioxide, and the depletion of water far beyond normal ranges. Estimating precise probabilities for these details is difficult, but together they point toward formation conditions unlike those seen in other objects. To this list, we can add the genuine forward-facing tail confirmed by Mars-based imaging, the jets that remain tightly collimated despite the object's rotation, and the unusually steep brightening observed on approach to the Sun. Each of these features is individually rare, but not impossible. Multiplying their estimated probabilities produces an extremely small number, a combined improbability that must be expressed in scientific notation because ordinary language cannot hold it. There are, however, important caveats. The anomalies may not be independent. An unfamiliar formation environment might explain several at once, reducing the combined improbability significantly. Some probability estimates rely on assumptions that might not hold for interstellar populations. Observational bias is another concern. Objects that appear ordinary may pass unnoticed, leaving us disproportionately aware of unusual examples. These points matter. They should temper our interpretation. Yet even after accounting for them, the sense of strangeness remains. The combination of features seen in 3I Atlas does not match any known profile of natural behavior. The question that follows is how we should respond when confronted with an object that appears to stretch or break our expectations. One answer is that the universe is enormous, and we should expect outliers. The mathematics of large numbers virtually guarantees that improbable combinations sometimes occur. In this interpretation, 3I Atlas is the statistical outlier we were bound to encounter eventually. It fits into a natural framework, though at its edges. Another answer is that when a pattern is dominated by improbabilities, we should consider hypotheses that make the data less improbable. This is not an appeal to speculation, but a form of reasoning used throughout science when existing models strain under accumulating exceptions. In the case of 3I Atlas, the alternative hypothesis proposed by some is that the object might not be entirely natural. A technological artifact could plausibly arrive in the ecliptic plane for observational reasons, time its approach for a sequence of planetary encounters, avoid detailed study at perihelion, and target significant gravitational boundaries like the Hill radius. A spacecraft could maintain precise alignment, produce tightly collimated jets, and adjust its trajectory during a period of limited visibility. Under that model, the anomalies appear less surprising, but considering an alternative hypothesis is not the same as accepting it. Extraordinary claims require substantial evidence. It is entirely possible that additional data from December and March will reveal natural mechanisms for each anomaly. Many unusual comets have eventually been explained through subtle chemistry, unusual structure, or unexpected but natural processes. Scientific caution requires that we keep all explanations on the table while waiting for stronger evidence. To formalize this spectrum of possibility, Professor Loeb has introduced a scale ranging from 0 to 10, where 0 represents full confidence in a natural origin and 10 represents full confidence in a technological one. Based on present data, he assigns 3I Atlas a score of 6, leaning toward artificial, but still far from confirmed. Many scientists disagree with this assessment. They point to the long history of extraordinary interpretations falling away once better data arrives. They emphasize the need for patience, yet even they acknowledge that some of the features described so far are difficult to explain cleanly. Science depends on the interplay between openness to new ideas and skepticism about extraordinary ones. That tension is not a flaw. It is the engine of progress. 3I Atlas has brought that tension into full view. We have data that is genuinely puzzling, probabilities that challenge coincidence, models strained at their limits, and alternative explanations that range from unexpected natural physics to intentional engineering. Only more observation can separate these possibilities. The December window will provide key measurements. The March approach to Jupiter will offer another critical test. Each new data point narrows the field of explanations. But until those data arrive, uncertainty remains. What we do know is that something unusual is passing through our neighborhood. A visitor that has triggered debates about probability, formation environments, propulsion, and the boundaries of natural behavior. We also know that the accumulation of improbabilities is not something we can ignore. Mathematics forces us to account for it. The combined improbability is a number too small to dismiss casually. What that number means is the question we must answer. And that brings us to the next threshold, March 16th, 2026. On that date, 3I Atlas will reach the gravitational boundary of Jupiter's domain, crossing a location defined by the Hill radius with a precision that has become the centerpiece of this entire investigation. Whatever happens at that threshold, whether nothing at all or something unexpected, will either close the debate or deepen it in ways that could reshape our understanding for years to come. The Hill sphere is not a physical surface. It cannot be photographed or measured directly. It is a calculated boundary, marking the region where Jupiter's gravity becomes stronger than the gravitational pull of the Sunday. Inside this region, Jupiter dominates. Objects can be slowed, captured, or placed into stable paths around the planet and its moons. Outside the boundary, the Sun controls the motion, and objects continue past without being trapped. At this same boundary sit two familiar gravitational equilibrium points, L1 and L2. These are locations where the forces from Jupiter and the Sun balance in a way that allows objects to stay in position with very little energy. Space agencies use such locations for long-term missions. The James Webb Space Telescope is positioned at Earth's L2 point for this reason. Any civilization with an understanding of orbital dynamics would recognize that the L1 and L2 points around Jupiter offer stable, low-energy platforms. If something were released from 3I Atlas as it crossed the Hill sphere, and if the released pieces slowed enough, they could settle naturally into these points. They would require minimal fuel to remain in place and could stay there indefinitely, with clear views of the Jovian system and the outer solar system. This remains speculation. There is no evidence that 3I Atlas will release anything. What we do have is the precise approach path, the measured course change during perihelion that produced exactly the needed arrival distance, and the statistical rarity of reaching this particular gravitational boundary so closely. These features have raised questions, but they do not confirm intent. Juno will be the closest operational spacecraft during the approach. From its orbit around Jupiter, it can observe the region where 3I Atlas will pass. Its camera systems may capture images that Earth-based telescopes cannot. Its particle detectors can sense changes in the charged environment. Its magnetometer can pick up disturbances in the magnetic field. If anything unusual occurs near the Hill radius, Juno has at least some ability to detect it. While Juno was not redirected to meet the object directly, it remains our nearest human-made observer during this event. The European Space Agency's JUICE spacecraft will also monitor the region. Though from much farther away, JUICE carries instruments designed for the physics of Jupiter and its moons, but they can be retargeted for other objects when needed. The combination of perspectives from Juno, from JUICE, and from Earth will help build a clearer picture of the encounter, even if the geometry limits what we can see. From Earth, observation will be difficult in March. 3I Atlas will be faint, far away, and moving against crowded star fields. This makes tracking harder, but major observatories will attempt it. There is a chance that Hubble could obtain images if time is allocated. Ground-based telescopes, equipped with adaptive optics, will try to capture any changes in brightness, shape, or activity. What could we see? The most straightforward outcome is that nothing unusual happens. 3I Atlas could pass through the Hill sphere without a change in activity, without fragmentation, and without any measurable acceleration. It could simply continue outward and fade slowly as it moves back into the cold regions of interstellar space. In this case, the precise arrival at the boundary remains a notable coincidence, something to study statistically, but not something that forces a new interpretation. Another outcome is that activity increases as the object approaches or crosses the boundary. It might break into pieces. It might brighten or release a new jet. It might show a shift in motion that was not present earlier. If fragmentation occurs, it could be due to gravitational stress or structural weakness. If a brightening event happens, It might be due to volatile material exposed by rotation or internal processes. If the motion changes, this would require forces beyond standard explanations and would demand additional study. There is also the possibility, still unlikely, but mentioned because the data has raised questions, that something occurs which cannot be explained naturally. This could include objects separating and slowing into Jupiter orbit, signals that resemble engineered emissions, or behavior that is inconsistent with any known cometary physics. Even if this scenario seems improbable, it cannot be dismissed entirely. 3I Atlas has already displayed properties that are outside normal expectations, and we do not know whether the pattern will continue. Waiting for the encounter is difficult. 4 months remain before March arrives. During this time, astronomers will refine tracking measurements, monitor activity levels, and compare models, but each week brings lower brightness and greater distance as the object recedes from the inner solar system. The period of best visibility is ending. The period of speculation continues. When the encounter finally comes, we may gain clear answers, or we may find only partial clues, leaving multiple interpretations open. Some discoveries are resolved quickly, others remain open questions for decades. The nature of 3I Atlas could remain uncertain for a long time, until future instruments or new theoretical frameworks allow us to understand what we are seeing. But this case feels different, partly because the implications reach beyond the object itself. If interstellar comets can vary so widely in their behavior, our understanding of planetary systems must expand. If, however, we are observing something technological that would reshape our view of our place in the galaxy, the possibility that other civilizations might send probes to explore regions around distant stars carries consequences that reach beyond astronomy. The date approaches. Jupiter sits ahead on the path, the massive anchor of the outer solar system. 3I Atlas continues along its trajectory, unchanged by our debate. Whatever it is, whatever has shaped its path, it will soon cross the boundary that has drawn so much attention. We will observe from Earth, from Juno, and from Zeus. The data will be collected, archived, and studied in the years that follow. Future researchers will have access to everything we detect, and they will judge what it means. For now, the threshold draws near, and we meet it with the same curiosity that has guided every stage of this investigation. Late at night, under a sky unchanged by our questions, we can reflect on the path we have traced. An object from another star has moved across our system after billions of years in interstellar space. It arrived from a direction near the source of the WOW signal. It aligned with the plane of the planets. It passed close to Mars, Venus, and Jupiter, while remaining hidden at the moment of maximum solar heating. It adjusted its course in a way that brought it to Jupiter's Hill radius with remarkable accuracy. We do not yet know what 3I Atlas is. We do know that the observations since July have revealed properties that do not fit easily into our current models. Jets that remain narrow when rotation should blur them. Chemical ratios that match no known population. A trajectory change during perihelion that produced the exact approach needed for the Hill radius match. Each of these may eventually find natural explanations. The universe is large, and rare processes do occur, but they also may point toward possibilities we have not considered before. Either way, the result matters. If the object is natural, it shows that interstellar space contains bodies far more diverse than we predicted. If it is technological, it shows that we share the galaxy with others capable of building machines that travel between stars. Thank you for joining me tonight as we explored these questions. Your willingness to examine difficult topics and follow the evidence wherever it leads adds meaning to this work. The discussion we have had reflects both established knowledge and areas where uncertainty remains. Scientific understanding evolves with new data, and interpretations may change as observations continue. Treat extraordinary ideas with appropriate skepticism while remaining open to new possibilities. The stars continue their slow motion overhead. Somewhere among them, 3i Atlas continues its path toward Jupiter and beyond. We remain a small species on a small world, but we continue to look outward, ask questions, and investigate the unknown. And sometimes, in rare moments like this one, something looks back